How does molecular orbital describe a bond? How does molecular orbital theory describe a bond? In other words, what constitutes a bond in molecular orbital theory? I'm sorry, can you repeat? Well, it's not necessarily constructive. I mean, that's how you make the molecular orbitals. You have the constructive, it's a linear combination. So you have the constructive and you have the destructive. But aside from that, how does molecular orbital theory describe a bond? I mean, it's a basic question. Why? I started off the chapter with why do bonds form? In the first place. Why bond? Why form molecules? Well, for bonding. Why? Because it's stability, more stable. But how does one describe a bond in molecular orbital theory? What exactly is a bond in molecular orbital theory? In other words, is valence bond theory and molecular orbital theory, in what ways are they similar and what ways are they different?
So they are talking about overlap
Rather than overlap, it's a combination, but it's similar in that way because the better the overlap is, the better the combination will be. So how would you describe a bond in molecular orbital theory? Why don't you go back in your notes and take a look and see if it's there or not? Maybe I said it about 3 times in class.
More bonding electron density?
Yeah, right. More bonding electron density than anti-bonding electron density. And so in that way they're very similar because the more bonding electron density you have, the more electron cloud you have between the 2 nuclei. In other words, we have a situation like this. So if we're looking at a bonding molecular orbital, we expect, either electron density within the internuclear axes. This would be called what type of molecular orbital if we had bonding density like that? Well, sigma, just a sigma. If the electron density were up here, is that bonding electron density or anti-bonding electron density? This is bonding electron density. How come? How does this hold the 2 atoms together, atom A and atom B? How are they held together? Yeah, the attraction with the negative electron cloud here. This is sigma attraction, this is a pi attraction. But both of them are going to result in holding the atoms or bonding the atoms together. How about this orbital here? There's electron density here and electron density here. Does this hold the two atoms together? No.
Wow.
Because the two protons, or the two nuclei, actually, let's erase the bonding. The two protons see each other. There's no electron density to hold them together.
But still, the
Still, okay, you're saying still there's this attraction here, right?
Yeah.
But you sum up the attraction, very weak, versus the repulsion, very strong. The repulsion wins out. And so what you should be focusing on is not the attraction, which is very, very weak, but the very, very strong repulsion. The thing is, this negative charge is, spread out over the orbital, here and here. Let's say we got two electrons. The electron density is spread out here and here, but the positive charge is concentrated in a nucleus. This is why, remember the Rutherford gold scattering experiment? The Rutherford gold scattering experiment, the electrons in the gold, like this, and then there's nuclei, like this. And then they shot alpha particles. You shoot alpha particles, you think, oh, it's going to get trapped in the electron density because electron density is negative, right? It's going to get trapped in electron density, but no, it just shoots right through. But if an alpha particle hits the nucleus, then it bounces off the nucleus. Why does it bounce off the nucleus? Not the density. It's not the density, because if it were just the density, it could stick. Have you ever thrown like a clay ball at a brick wall? The brick wall is very dense, but the wet clay ball sticks to it. It doesn't bounce off, right? It's not because of the density, it's because of repulsions. This is positive, they're going to repel each other. In fact, it's not even going to hit it. The repulsions are going to get so strong, it's going to bounce off before it even hits it. Probably. It depends on how much force. I mean, you could, if you used a linear accelerator or something, you could force it in to the nucleus to overcome the electrical repulsions. This is a nuclear reaction there. A nuclear reaction. Whereas neutrons, you know what? Neutrons will collide with the nucleus and stick. Why? Because neutrons have no repulsions. That creates a big problem, because if neutrons come in here and collide and stick, they make the nucleus unstable. And so neutrons tend to turn things or make things radioactive. And so if you work with neutrons, if you're using like metals or whatever, pretty soon the metals are all going to need to be replaced, because well, anyway, getting back to this, it's the repulsions that you should see are significant. And so as long as we have more attraction, as long as we have more bonding electron density than anti-bonding electron density, then there should be a net electrical force holding the two atoms together, and that's a bond. In valence bond theory, how's a bond described? In valence bond theory, it's exactly the same. You have electron density in the internuclear or region. It could be along the internuclear axis, sigma, or it could be above and below the internuclear axis, pi, right? But it's exactly the same thing, because in valence bond theory, what you're doing is you're just concentrating the electron cloud between the two nuclei, which means you have net attraction here, right? And so this is why when we're doing valence bond theory and molecular orbital theory, why I wasted all that time doing all the electron dots. I wasted all the time doing all this electron dots because this is what holds the molecule together, you know? Having more of these dots in here versus out over here, the anti-bonding, you know, that makes a difference. And also the orbitals, you know? And so basically it's kind of the same thing. We're just looking at how the electron cloud is distributed in the molecule using valence bond theory and MO theory. Okay, but they're going to show slightly different electron cloud distributions because you know, one shows the electron cloud distribution retaining atomic orbitals and overlapping them. The other gets rid of the atomic orbitals and replaces those with molecular orbitals. And so the explanation I get the most, why how is a bond described in valence bond is the overlap of atomic orbitals, but that's not complete. You know, the overlap of atomic orbitals increases electron cloud density between the two nuclei, thereby holding the atoms together by electrical forces. The answer for MO theory is, a lot of people say, well, two atomic orbitals combine to create molecular orbitals, and molecular orbitals hold them together. Well, not exactly, you know. We have to have more bonding electron density than anti-bonding electron density for the atoms to be held together. Okay. They're both electrical in nature. So, speaking of valence bond, I mean, can you do a valence bond analysis of some Lewis structure, you know, figure out the hybridization, draw out the orbitals, you know, overlap them? Can you do all that stuff? Yeah. What do you think? Do you think I'm going to ask that on the test? Yeah. And so you should be able to do that, and then, you know, do you think you're going to have to show like a double bond, maybe a triple bond? You know. Can you do that? Can you show me a double bond, top view and side view? Good. How about a triple bond? We just did a triple bond yesterday, I think. Did we?
The PD bond.
Oh, the PD bond is something else. PD bond is a double bond, usually. A PD bond, you aren't going to have a triple, that's for sure. Yeah, 2 pp pi bonds, usually. 1 sigma and 2 pp pi bonds. This is a typical triple bond. Like carbon monoxide, I don't know if we did that. Did we do carbon monoxide or cyanide or one of those? Yeah, okay. So you'll have to do valence bond and show some drawings, and can you do the energy level, orbital energy level diagram, you know, for the hybridized? So, good. And then MO theory, you'll have to know the diagrams, you know. The diagrams. You know, the patterns. Do you recognize this pattern? Pattern is that the Z lithium. And then this part stays the same. It's just this. Z greater than 8. And so you could just remember, you know, these triangles like this, and then you just flip one of them upside down or something. You know, you start it like this, and then, or have some other way of remembering it, you know. And people have different ways of remembering it.
We also have the other the heterogeneous, like carbon and...
Yeah, well, except you don't have to label it, you know. These you have to label. right? But for the heterogeneous, like carbon monoxide, carbon's less than 8, oxygen is equal to 8, which means carbon, you're supposed to use this, oxygen, you're supposed to use this, so which one do you use? The lower one, carbon.
In the solution manual, there's an example where they use the higher one.
The higher one, which molecule?
I think it was CO. CO.
CO, they use the higher one. All right. Let me say one other thing. Some books don't have you memorize 2. Some books will only have you memorize 1 and say it doesn't make a difference. And so let's use both of these for oxygen. Oxygen has how many valence electrons? O2. 6, and we have 2 of them, so it's 12 electrons. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so if we use the Z8, what do we get for the bond order? This is our antibonding here. 2. Is it paramagnetic or diamagnetic? Paramagnetic. Okay, what if we use this one? What do we get for the bond order for oxygen? Well, it's paramagnetic, and we get a bond order of 2. So after looking at a lot of these molecules, they realized, we'll get the same, for these. The only difference is, for excited states or ions or something like that. And so some books, they only use one of the diagrams and just say, okay, we're going to use this one, and that's it. And even though it's not right for, let's say, Z less than 8, we'll still use it.
So you're saying that if it's heterogeneous, both atoms have to be at least 8 protons in order to have the second one?
Yeah.
So if at least one of them is less than 8, then we go with the lesser one.
Right, because you weren't given a rule, right? Were you given a rule for... I mean, if you notice this, what did Petrucci use for carbon monoxide in the chapter? Which one did he use?
Less than 8.
And so you're saying in the chapter he used the one less than 8, in the homework solutions manual he used the one greater than 8?
But you used in 2 examples. One of them used less than 8, while the other one used more than 8.
Okay, what was the other one? What was the other molecule?
It was the same CO. One example used CO was lesser, and the other one used this as more.
Well, let's take a look at that one specifically.
I don't have the solution manual, so.
Well, that's okay. Well, I mean, I want to look at the problem itself.
One of them was in 35.
Um, 35. Write plausible molecular orbitals for the following heteronuclear diatomic species. This one? All right. Well, let's look at CN. Which would you do for CN?
Less than 8.
Less than 8. Both of them, right? Less than 8. CN minus?
Less than 8. Less than 8. Less than 8.
NO. Well, on the one hand, nitrogen is less, oxygen is equal. And so for NO, well, one says we use less than 8, the other says we use 8, right? Now, we don't have a rule set up. And so since carbon monoxide was that, then we'll just use the same. Just keep it simple.
This is the example where the solution manuals use the less than 8 for all of those.
They used it for all of them?
I think so, yeah.
If they use it for all of them, then that's okay, because CO, they used it earlier. If they use less than 8 here, then they're being consistent at least. I thought they weren't.
No, I mean, I don't know. Can you went to the solution manual?
Okay, if they're being inconsistent, then they should tell you why.
I just remember there were 2 problems, and one of them they used lesser, and the other one they
They use greater? Which? Okay.
I'm looking for the other one.
Okay.
But I don't know which one was which.
Okay. Well, we'll just be consistent. We're going to use less than 8. All right, so that's the whole MO valence bond stuff. You just have to have it, memorized. The orbitals are, and how to draw them out, and that kind of stuff. You don't have to memorize the orbital shapes for MO, though. I'm not going to make you draw those. I just did it, and I asked you to do it as an exercise to see, do you get more dots in the bonding or less dots in the bonding than the anti-bonding? That's what creates the bond. All right, other questions?
Could you quickly go over the shielding?
Shielding for which example?
Beryllium.
Beryllium versus,
Oh, just, the Z is a Z effective.
okay. So beryllium has how many protons? 4 protons. So Z for beryllium is equal to 4. So it should have a +4 charge. Beryllium has a 1s electron. 1s electron, how much charge will this electron see? It's a 1s electron. How much Z will that electron see? Just this 1s electron. +4. What is the Z effective? +4, because there's no shielding. And so if it has 1 electron, there can't be any shielding, right? Well, 1s orbital holds how many electrons? 2. So if we put a second electron in there, what is Z? Well, Z is 4. What is Z effective? About 4. It's going to be a little less than 4 because sometimes this electron will pop here and shield it. And so Z effective is for one of these electrons is going to be less than 4, a little less than 4. Does that make sense? Okay, what's the next electron? A 2s electron. A 2s is in the next shell. And so these are now called inner shell electrons. Inner shell electrons, are they effective shielders? Yes. The inner shell electrons are blocking out the charge from the outer shell electron. They're shielding. And so if this were +4 and you have -2 plus 4 minus 2 is going to be about plus 2. So Z effective is about plus 2. In fact, we'll just call Z effective plus 2 to make it easier. Okay, now, if Z effective here is plus 2, we add another electron in the 2s orbital. What's that going to do? Well, we're going to go from a Z effective of about plus 2 to a Z effective a little bit less than 2. And so Z effective here is going to be about 2. Actually, less than 2, let's just say. That's it. I actually have the Z effective numbers written out. I thought I'm not going to write them down. Just more numbers.
What if we go to 4 and we have a p orbital for the 5th electron?
Okay, for the 5th electron, the p orbital is about the same size, kind of, as a, because they have the same, what we call the same, what did I call that? Effective distance. And so the p orbital is considered same shell, even though, it's different. And even though the penetration is different, because the 2s is much more penetrating orbital than the 2p. But as far as shielding goes, we're going to say it's about the same. It's same shell electrons are minimal. And so, but the 2s are going to be more effective at shielding a 2p. And so, Z effective here should drop even more than before. But, it's still around. What would Z effective be? Now Z effective would be around, well, the 2 inner shell electrons drop it down to 2, so it's going to be, this was a little less than 2, and this is going to be a little more less than 2. In other words, in other words, the same shell is about, it's actually, when I say not a very effective a shielder, if you did the Slater's, did anybody do the Slater's rule problem in the homework? Nobody did that? Actually, I forgot what problem number this was. Can I search this? Okay. Let's just take a look at this. We have seen that wave functions, etc. Slater devised the following set of empirical rules to calculate a shielding constant for the designated electron in the orbital NS or NP. So we write out the electron configurations. Electrons in groups to the right of the NS-NP group contribute nothing to shielding. And so electrons that are further out aren't going to shield any electrons that are further in. They're just farther out. Their effective distance is farther out. Electrons in groups, I just read that. All the other electrons in the NS-NP group shield the designated electron to the extent of 0.35 each. This is same shell. same shell electrons, when I say the shielding's minimal, it really isn't. It's 35% shielded. And so this electron here, because of having this electron here pop in, is going to reduce it by 35%, the charge. And so it's 35% shielding, but I didn't talk about that because it's more than I wanted to discuss. All electrons in N-1, and so the shell immediately below this shell doesn't shield 100%. It only shields 85% here. So the first inner shell shields 85%. And the shells that are inside deeper will shield 100%. And so all electrons in the N-2 shell, that is 2 shells in or lower, shield completely. Their contributions to the shielding constant are 1. In other words, 100%. And so if I'm a 3s electron, the N=2 shield 85%. This is how it works. If I'm an N=3 electron, the other N=3 electrons shield 35%. The N=2 electrons shield 85%, and then the N=1 electrons shield 100%. But, you know, Slater's rules are empirical rules, you know, and so we just made some very qualitative. I just made this easier. The way I made this easier is just, okay, inner shell electrons shield effectively, same shell electrons shield ineffectively, and we're just guesstimating the charge. Okay. These things can also be calculated, not empirically, but these can be calculated using quantum. All right, these rules are a simplified generalization based on the average behavior of different types of electrons. Use these rules to do the following. Calculate Z effective. Calculate Z effective for copper. Calculate Z effective for 3D copper. Evaluate Z effective for the valence electrons in group 1. Energies observed, Slater's rules. And so, you know, you could dig much deeper into the shielding if you want by just doing one of these. By doing one of these, then you'll get a much better idea how Z gets cut down, you know, by the electrons. This is an advanced exercise. That's how, if you want to know shielding in detail, you do this number 73. Then you'll know shielding in detail once you work through a problem like that. All right, other questions?
Would you consider eliminating the paper?
Eliminating what?
The paper.
Yes. Give us another test.
No. Can we just turn in the worksheet for that?
Why do you want to eliminate the paper?
It's a lot of words.
A lot of work.
Yes. Please.
That's going to be a tough thing because every semester I can't make it. I know it's a lot of work. Doing the paper is a lot of work. Yeah, but you should do something, some kind of written lab
Can
report.
you just make it a whole class assignment then?
No, I'm sorry. There's no time to do it. Is that it?
Yeah.
No.
Even after the final? I mean, after the due date is after the final on Monday, right?
Well, my partner's flying out to Japan like the day after.
The day after. Well, you know, I could just give everybody the same grade, you know. It'd be just a C.
No.
Yeah. I get a C. Average. I'll just call everybody average.
Hey,
I think we could forget about the final as well.
Oh, really?
Just, give everybody a C on the final.
You can do
that.
It's better than a D or an F, huh?
No.
That's true. Yeah, the paper is something I've done every semester. And so, yeah, I understand. Just turn in the best you can do. Let's see what that is. The paper doesn't take, well, the first time you do a paper, it does take some time. Especially if you don't know some of the stuff. We can talk about the paper if you want.
We talk about the paper.
Can I talk about it tomorrow?
Yeah.
If it's
After the
that's
set.
tomorrow, so.
All right, then what do you want to talk about today?
And the basic question that you were talking about earlier.
Will you have this?
Oh,
compute
Can you
stuff
explain
with
the antibody orbitals? What does it mean for them to be out of phase with each other? What is that?
Well,
Yeah. It's a computation like that.
are those in phase?
Yeah.
How about those? Are those in phase? No, those are out of phase. That's what it means. That's one way of thinking about out of phase. The other way of thinking about out of phase is like this. Let's take a p orbital. The p orbital, let me ask you this. Do you know what the color code on the p orbital means? One of these is red and the other is blue. Positive and negative. Doesn't matter which one's which. Where do these positive and negative come from? Let's call this the positive y direction here. This is x. This is positive y. And so what does the wave function look like? This is positive amplitude. This is negative amplitude. And so if we do this, the orbitals are in phase. If we do this, the orbitals are out of phase. So that's all it is. Are they in phase or out of phase? When you have a positive wave interacting with another positive wave, the wave amplitude grows. If you have a positive wave and a negative wave, have you noise canceling
Yeah.
headphones? They try to cancel out the waves. How do they try to cancel out the waves? Cancel out the waves by, if you have noise like this, you can cancel out the noise by just having it out of phase slightly. It'll cancel it out. Another signal out of phase.
So do we need
The
to
noise
perform the signal?
I'm sorry?
Do we need to give the signal frequency of the alpha?
The same frequency? Yeah. Yeah, to cancel it, it would have to be the same. Let me take that back. Not exact. I mean, even if it's slightly off, it'll cancel. Depending on how long it goes. If it's a standing wave, we'll reduce it. And so anti-bonding is, they're out of phase, so they don't add up. So we get this. This is why I think, drawing the MOs is not difficult if you know a little bit more. If you know a little bit more, the positives and the negatives will add up. Right? Like this. Whereas this is called the pi bonding, pi 2p. This is called the pi star 2p, plus and minus. Out of phase. They don't add up. This is a node here. So this would be anti-bonding. We're not going to get any electron density. Put this in here. Get that out. So does that answer your question about?
Well, I'm just wondering, like, physically, why do amplitudes that are in phase correspond to density between the atoms, and waves that are out of phase correspond to densities that are destructive? Well, not destructive, but anti-bonding. What's actually going on?
This is the easiest one to see. What happens if you mix these two waves together? Do they cancel? What happens if you mix these two waves together? This is positive, this is positive. The positive is going to, oh, this is constructive, right? What happens if you try to mix these two together? They cancel in the internuclear region. Do you see the positive and negative are going to cancel each other out? They cancel each other out. This is positive, this is positive. How is this electron density, if there's electron density here, going to hold the two nuclei together? That's why that's called anti-bonding, because rather than pulling them together, there's repulsions pushing them apart, which is anti-bonding. Bonding is pulling the two nuclei together, holding them together. That's how. Does that answer your question?
Well, what is the difference between negative amplitude and positive amplitude in terms of the electrons? What are those two things that go? What difference does it make?
Well, that's back in chapter 8. It's wave. Let's look here really quick, and then we can discuss this more after class.
Okay.
Move on to this next thing, but what does negative and positive amplitude mean? Let's see, maybe there's a video on this. look at how those two waves interact with each other. You see where there is peaks. The peaks will grow. Where there's valleys, these are two water waves interacting. You see the interference pattern? The new one's being generated. Let's see. I'm actually going to show a video on Tuesday. Showing X-rays. Let's see if there's an animation here. If you just look at electrons a wave, right? And so if you have positive amplitude here, let's have two waves. We have positive amplitude here, and a second wave comes along. If the second wave is in phase, then the waves grow. And so this is like, okay, a boat. There's a boat in the water and it's creating a small wake. But there's another wake out here that's created by a big boat, and let's say they're in phase, so what happens is the waves start to grow, right? Versus if the two waves are out of phase, then they'll cancel. So this one's generating a valley as this one's generating a peak here. Then what's going to happen? The positive amplitude and negative amplitude will cancel each other out. But if this one's generating a peak at the same time this one's generating a peak, then the positive amplitude will increase the size of the wave, the water wave. And so just experiment with this. I don't know, unless does somebody have an easier? Here, there's two waves being generated. Oh, this is probably not the easiest video to see. Well, we could talk about it later.
Yeah.
People don't get it. Are there other questions?
On this practice test,
Uh-huh.
there's a question about which species is the most basic.
Okay. That's something I skipped talking about. But at the end of chapter 9, there's periodic properties. And so metal oxides are basic. Non-metal oxides are acidic. And so I only talk about non-metal oxides like CO2. CO2 is an acid. Calcium oxide is a base. That. And then semi-metal oxides are in the middle. Yeah, those are amphoteric. Oxygen's not a semi-metal. Oxygen is a non-metal. And so non-metal oxide should be acidic. H2O is acidic. Right? But H2O is also amphoteric. H2O is special in its properties. The semi-metals are going to be on this borderline here. What are the semi-metals? The semi-metals: boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium. These are the semi-metals. And the semi-metals are going to have properties of both metals and non-metals. It's in the transition region. And so semi-metal oxides, like aluminum oxide, would be amphoteric. And Al2O3 should be amphoteric. Normally we think of aluminum as being a metal, and you're right to think of it as a metal, but aluminum oxide has some other properties as well. One of them is that aluminum oxide will react with acids and it will react with bases. But it turns out it's not very reactive because aluminum oxide has an incredibly strong bond. Why is the bond so strong in aluminum oxide? Aluminum oxide, it should react with both acids and bases, but it turns out to be pretty inert. You know, aluminum oxide is found in nature. It's called bauxite. It's an aluminum ore. And some of these tropical islands consist of a lot of aluminum oxide, a lot of bauxite. Problem is extracting the aluminum from bauxite, the ore, you know, it's so unreactive. Even though it should be amphoteric, it should react, you know, but it doesn't because the bond is so strong that the person who figured out how to get aluminum oxide to react without too much difficulty became one of the richest people on Earth at the time. Maybe he was the richest person on Earth at the time, you know, at the turn of the century. This is a very interesting documentary if you ever look for it. It's about processing aluminum. You know. Aluminum used to be a very rare metal, but now much more common. So why is the bond so strong in aluminum oxide? Because of resonance stabilization? What would you say? Aluminum oxide is more ionic or more covalent?
More ionic.
More ionic. So what holds? In other words, what makes an ionic bond?
Positive and negative charge attraction.
Exactly, positive and negative charge attractions. So tell me why aluminum oxide is such a strong bond.
I guess like aluminum ion is like electron rich, like more electron rich.
Aluminum is not electron rich. How can you call aluminum ion electron rich if it has a 3+ charge? You know, is that electron rich? No, I wouldn't consider it electron rich. We don't necessarily talk about, you know, when we're thinking about ionic bond, we don't necessarily talk about electron rich and electron poor. We usually talk about, remember Coulomb's law in the beginning? We talk about the charge on the charge on the I don't know if you guys remember this. I did examples earlier. Lithium chloride versus sodium chloride. Way back when. You know, which would you expect to have be a stronger bond? Lithium chloride or sodium chloride? Why? No, that's not the reason.
But they're not even.
Lithium is smaller.
Lithium's smaller. I talked about charge density, charge to size ratio. Long time ago. You know. I understand you got a lot to worry about with the final coming up, and so it's probably a lot. But you know, the paper serves another purpose. The paper gives me a little bit, you know, of insight into your understanding of chemistry. You know, how well you understood the lab, you know, that particular lab, and so this is why I want to see, you know, it's not, okay, lithium chloride is, but it's lithium chloride because lithium's smaller ion, you're going to have a higher charge density, which means a greater electrical force, right? Greater electrical attraction. That's it. And so something like aluminum oxide,
The size.
well, this is charge to size ratio. Aluminum 3 plus is extremely small and it has a very high charge. How many 3 plus ions can you name off the tip of your tongue? Aluminum 3 plus? Iron 3 plus? Not that many, right? And so this is very high charge. Very high charge, small size, oxide, high charge, therefore it's going to be a strong ionic bond. And so this is why the guy became incredibly rich, because, how do you break that bond? You could try to melt it. But you know what the melting point of aluminum oxide? If you expose aluminum oxide, you might know this stuff. It's called alumina. It's a wonder ceramic. I used to use alumina cookware, because alumina cookware you can heat to 1,000 degrees C, no problem. It doesn't vaporize. It doesn't decompose. Stuff. Just about everything else inside vaporizes. But you used to use aluminum pots. You can't use a metal pot. A metal pot would just melt at very high temperatures. And so we use that. Aluminum oxide is used for goggles for nuclear bomber pilots. They have aluminum, single crystal aluminum oxide, extremely tough material. And then they dope it with impurities so that they can apply voltage. And when they apply voltage, it blacks it out completely. But single crystals of aluminum oxide are totally transparent. But, okay, so anyway, this particular question, I skipped it, so, whereas in that semester I talked about it. This semester I decided to skip a lot of the Lewis acid-base stuff, whereas in that particular semester I talked a lot about Lewis acid-base stuff. I figured I'm going to move the Lewis acid-base stuff mostly to Chem 1B. A lot of other instructors don't talk about it at all, Lewis acid-base. This semester I decided that I'm going to spend more time on this orbital stuff because organic chemistry, I heard from some of the organic chemistry instructors that some of the students are extremely weak in understanding valence bonds, orbitals, hybrids, this kind of stuff, structure, geometry. So I thought, okay, this is probably more important than talking about some of this stuff in chapter 12, 12. Oops. Let me give you a quick preview of the latter chapters. We still have chapter 12 and chapter 13 to talk about, but chapter 12 talks about the properties of liquids. What are the properties of liquids? Boiling point, freezing point.
Melting point.
Well, melting point is usually for solids, and so that would be here, melting point. But melting point and freezing point are the same thing, the exact same temperature. We have some others. Some other properties would be viscosity. Have you heard of viscosity? It's like really viscous stuff don't flow very well, like honey. And so viscosity, all these things are related to intermolecular forces. There are only 3 intermolecular forces that we need to talk about. London, aka dispersion, aka induced dipole type. What is it? No, instantaneous induced dipole. Have you heard those? London or dispersion forces? Dipole forces and hydrogen bonding. So we'll talk about intermolecular forces and how they relate to the properties of liquids. And then some properties of solids, melting point. What else? Okay, that's about it. And then phase diagrams. Have you ever heard of a phase diagram?
Yeah.
Phase diagrams tell you, under what conditions of pressure and temperature that a particular phase is stable. And so, Under certain conditions of temperature and pressure, gaseous phase is most stable, and liquid phase is most stable, or solid phase is most stable. There's another phase here called a supercritical fluid. Supercritical fluid is a hybrid between a liquid and gas, so it has liquid properties and gas properties together. And supercritical fluids are dense like liquids, but they expand to fill the volume like gases, and so they have a lot of applications. One application is supercritical CO2 is used to decaffeinate coffee. They're using it for dry cleaning now, etc. And so these are phase diagrams. We aren't going to spend that much time. Those aren't too hard to understand. And then 12.5 through 12.7 deal with crystals. Now we have network covalent crystals, ionic crystals. We also have molecular crystals. And so we're going to be looking at crystals. In fact, the lab on Tuesday, we're looking at crystal structures. We're just going to look at a couple of crystal structures. Okay. And so that's chapter 12. And then in chapter 13, we're looking at solutions. You know, solution concentration, like molarity, percent, composition, something called normality, which we aren't really going to spend any time talking about. Intermolecular forces in the solution process, you know, because we got to break apart the hydrogen bonding interactions holding water to put sugar molecules in there. We got to separate the sugar molecules from each other. Sugar molecules are held together in the crystal by intermolecular forces, not bonds. And then we create these. These are solvated or hydrated sugar molecules in the liquid phase. And so we'll talk briefly about the solution formation process, which is, you know, dissolving the solute in the solvent. Then we'll talk about solubility, you know, and temperature. For example, is sugar, this is a sugar cube, is it more soluble in cold water or more soluble in hot water? And it's actually, sugar cubes are actually more soluble in hot water, so we'll talk about why that is. You know, whereas something like CO2, you know, CO2 gas, is it more soluble in hot water or cold water? Cold water, yeah. Or oxygen gas. You know, if the temperature of your fish tank goes too high, then you're going to lose a lot of oxygen out of there. Fish could die. And so, you know, gases and solids are different. We're going to talk a little bit about vapor pressure. Vapor pressure is a property of a liquid. Vapor pressure, you know, things with high vapor pressure are very, very volatile. Have you heard of volatile? Volatile just means it evaporates rapidly and easily. Things with low vapor pressure are fairly non-volatile. They don't really evaporate that well. And those are related to intermolecular forces. And then the last part of chapter 13 deals with something called the colligative properties. Colligative properties include osmotic pressure, freezing point depression, boiling point elevation, and things like what happens if you add sugar to water. Does water still freeze at 0 degrees? No, it actually freezes at lower temperatures. Does it still boil at 100 degrees? No, it actually is going to boil at a higher temperature. And then colloidal mixtures. Colloidal mixtures are at the border between a solution like sugar water and a suspension like muddy water. You know. Colloids are like milk. You know, they have very large solute particles, but they don't settle down to the bottom. But those large solute particles scatter light, so you can't really see through it very easily. They're more opaque rather than totally transparent. And so really, there's not. What we're going to do with chapters 12 and 13 is we're just going to do a brief outline of the important points in this chapter. But a lot of this stuff is not terribly or conceptually difficult, like, you know, this valence bond stuff in the MO. A lot of people end Chem 1A without really understanding what valence bond or MO, or even understanding the difference between valence bond and MO. You know, if you take a survey of a lot of Chem 1A graduates and ask them what's the difference between valence bond and MO, can't answer it. It's not good not to be able to answer that. Or, how does an MO, create a bond between two atoms, that kind of stuff. So we'll talk about that. And then this phase stuff is, phase stuff for advanced organic is super important. This positive and negative phase, because the positive and negative phase creates differences in what we call stereochemistry, how things are bonded together. So for example, wood is made up of glucose. Glucose is sugar, right? And so if wood is made up of glucose molecules all linked together, wood is a polymer, they call polymer glucose molecules, then why can't we eat wood? Because glucose is sugar, glucose should be fuel. We should be able to power our bodies using cellulose, cellulose wood. Right? It's because of how it's bonded together. How it's bonded together really depends on this kind of stuff. If you take advanced organic chemistry, when I'm saying advanced, if you go on to organic chemistry, this would be like a 7B here, then you got to know this. You got to know this stuff because this is what creates different arrangements and bonding, which means you either can digest it or you can't digest it, even though it's made up of glucose. And so one of the complaints that I got was that students aren't coming in prepared for this. They don't understand it, and therefore they struggle. And so therefore this semester in particular, because I just heard this last semester, this semester I spent a lot more time on this than I normally do, because it's so important. Whereas this stuff isn't so, I don't get complaints. The students aren't understanding boiling point elevation, or freezing point depression. I get the complaints, students don't understand thermo, going on. They don't understand this, going on, and it hurts them. It makes the attrition rate high. So you might think I'm shortchanging this. I purposely shortchanged this because I didn't think it's that important. Okay, that's the reason why. What's that? You have to study for the final. But,
Chapter 12.
12 and 13. But the thing is, remember what I said? This is why coming to lecture is important, because the people who skip out on lecture don't know what I think is important in 12 and 13, so they have to study all of it, all of it. And they don't know in how much detail they should know it, right? And so for chapter 12 and 13, basically you don't even have to read the book. As long as you just understand the stuff that I talk about in class, then you're all right for the test.
So our Chem 4 understanding about it, okay, is he not?
Yeah, except a couple of things that have to go beyond Chem 4. But, a lot of this stuff was talked about in Chem 4. You should have heard about vapor pressure. You should have heard about, but some of these things you might not have heard about, and some we're going to get into a little bit deeper. The only thing we're going to get into a little bit deeper is some of the thermodynamic calculations. Like in Chem 4, actually you do talk about. But when I talk about thermodynamic calculation, let's talk about solute formation. Does it cost energy to separate the glucose from the crystal? Breaking these off, does it cost energy? Yeah. Does it cost energy separating the water molecules from each other to make room for it?
Yes.
So if you pull apart two water molecules, does that cost energy or does that release energy? It could cost energy because you got to break hydrogen bonds. And so this costs energy, that costs energy. Where do you get the energy in return, if any? You get the energy in return from forming sugar-water interactions here. And that returns a lot of energy. So breaking solute-solute interactions, endothermic. Breaking solvent-solvent interactions, endothermic. Forming solute-solvent interactions, exothermic. But there's a trick here, because if the whole process, when you do Hess's law, and the whole process comes out net exothermic, then we say we're going from something less stable to something that's more stable. But sometimes, a lot of these solution processes, you're going from more stable to less stable. In other words, you're going uphill. And so when we try to dissolve certain solutes in water, have you ever felt it? It starts to get cold as it's taking in heat from the surrounding. But the thing is, why does that happen? Because we're going from lower, more stable, to higher, less stable. And so in this chapter, we have to introduce one more driving force in nature. There's actually one way of thinking about the driving forces in nature is that there are two driving forces. In Chem 1B, we'll see that the two driving forces are in fact the same. But the second driving force in nature is called entropy. And so in this chapter, we just briefly talk about entropy. I don't think they talk about that in Chem 4. And so you could have an endothermic, just slightly endothermic solution formation process, but it's going to occur because the entropy increases. And now entropy is a measure of disorder. So this crystal is very well ordered. The water, pure water, is pretty well ordered for water. But when you dissolve this and break this in, it becomes more disordered. And as it becomes more disordered, the entropy increases, and therefore that drives the solution formation process in addition. And this is another reason, like gas formation. Gas formation also drives it because that increases the entropy of what you had before. And so this is Chem 4 plus entropy, basically. I'm going slow right now because I was keeping the classes in sync. I didn't want to go too far ahead in this class compared to the others, but I had a lot more questions in the morning class. And so I can talk about more things if you want me to review something for the test, I can. Otherwise, I'm going to jump into this. Now, what do you want to do?
Well, you briefly just talked about the ionization energy stuff. We didn't really do much computation.
We don't.
So,
Yeah, we don't do much computation with that. If you look on, I don't know, on the practice exam, did I have you do an ionization energy?
well, you just asked me which has the highest.
Yeah. Just understand qualitatively. Yes or no?
So how will you do the final? Will it be the same, like 35 questions?
No.
Choice.
Mostly multiple choice, but more like 60 questions. The final question is longer. Final exam's longer, so there should be more questions in final. It's going to be like 60 questions. The final exams are worth twice as much, right? And so the questions are going to be worth more like 3 points apiece. And then there's going to be some other stuff on the final. Yeah.
Like
Such as?
diagrams?
No, I didn't mention it before.
No.
Equations, reactions, equation writing. You're going to have to do that. Write out the products for. That was that's another thing that I changed. When I first was teaching general chem, it was much more theory and physics, but the students were coming out very weak in actual chemistry. What happens when you mix these two things together? Do you have any idea what's going to happen? And so this is why I'm emphasizing chemical reactions, because chemical reactions, the physics stuff you can get in physics as well. It's very similar. But the chemistry stuff you aren't going to get anywhere else. We talked about metathesis reactions, redox reactions, Bronsted acid-base reactions. So on the final, you could expect What? Metathesis reactions, redoxin, acid base. Although, I mentioned it, I thought I mentioned it before the exam too, that you could expect metathesis,
You might have.
redox, and Bronsted acid base, but the Bronsted acid base, I was surprised how few people got the Bronsted acid base. Only like 3 people or so got it. So take a look at Bronsted acid base again. Make sure you understand it. It's not hard once you've done a few of them. All right, let me talk about the paper a little bit then. Yeah, the paper, I assume everyone's already done the calculation, right? Actually, I looked at a lot of people's numbers, and some people were asking me what to do about a big 95%. The numbers were quite scattered. I mean, that's the hand that you were dealt with. So this is why it's a good thing that we have a paper like this. With a paper, you can say something about it, If you were just to turn it in, this is my average and this is my 95%, then I have to weigh the 95% much more heavily as far as your points go for this lab. And also, let's say your percentage was way off. The actual percentage was this, but you got something that's way off. Sorry. Then, your grade, if you just turned in the paper, with the calculations and the numbers, then your grade is going to be based on how accurate you were and how precise you were. Accuracy would be the percentage difference. Precise would be how big your 95 or how small your 95% came out, right? And actually, I've done that in the past, and but in this, if you do the paper, your points are going to be distributed more, towards not just your accuracy and your precision, but also what you wrote about it as well. There is your accuracy and precision will still be graded, but not as severely for that.
Can you bring up the examples next time? So we can have a look through.
Can you maybe bring them tomorrow so we can look at them?
Tomorrow's the test, right? Yeah, so we could look at it before if you want the test. I could show you the examples of that.
Will we have a review day before the final?
Some people have actually completed a lot of the paper. I've reviewed some, a little. They already got started writing the results and discussion and that kind of stuff. So, it's something that I can't just cancel right now because some people have already invested quite a bit of time. Plus, it's important to do. But if you're going to, if somebody's going to be leaving on Friday, maybe you can correspond by email. That's one thing. Or maybe you can complete it. I actually get a lot of papers on Thursday. In the past, I've gotten a lot of papers on Thursday because they're planning to leave on Friday and not wanting to think about it at all. So they completed it before the final. But considering that a lot of people haven't even finished the calculations on experiment 2, I wasn't so optimistic about this one.
If we turn it in on Monday, or can we just email it to you, or we have to bring your copy?
The hard copy is preferred. I did take emails at one time, but some people's emails, the format, I couldn't open in my version of Word. And then I tried to contact them, and they never replied back. And I had to give them an F on the paper because I couldn't open it. And I was thinking, oh my, that was, but I mean, and then I thought, oh, okay, they're going to contact me afterwards, but they never contacted me. And they didn't pass the course either, but it could have been because of the paper alone, They might have been able to pass. And so I don't, that's the reason I don't like, I like paperless. I like the whole idea of paperless. I don't like the waste.
Well, if we send you a Google link, you could view it from any computer, the document.
Well, you can send it PDF, but, what I'll end up doing is printing it. I want a hard copy. I just want a hard copy. You can turn it in any time before the office closes. The office closes at like 4:30 or 5, and just leave it with them. They're familiar with this routine because every semester I do the same thing. Now I've collected it after the final because everybody wants it extended, and so they know what to do with the papers. They'll just make a box for me and collect them all in a box. That's it.
And then you said experiment 2 is due next week too?
Experiment 2 is due next week too.
Tuesday or Monday?
Tuesday. Take a look at those calculations. The calculations don't really take that much time to complete.
Will you be in your office after the test tomorrow, so we can ask you about the paper?
I'll be in the lab after the test. There's probably going to be people there. You can ask me about the paper. Just bring in your rough draft. You can take a look at it if you want. I've already looked at a couple of rough drafts so far. So if you have one, if you don't, whatever. Ask me on the other thing is, I'm always kind of wary about showing you, because past papers. If I show you the top past paper, then the bar has just been raised. I expect you to do a little better than the past paper, because you already see an example, right? And so if I were to hand out a paper and then you just copied it, kind of thing, then I'd want a little bit more, something original in there. And so this is why I'm not going to hand out sample paper, because I don't, these aren't going to be graded too severely. This is the first paper, as I said before. I used to collect 3 papers in Chem 1A, but it was too much. And so it's dropped down to 1. In Chem 1B, there are more papers. In Chem 1B, I collected 3 papers.
You're going to do that next semester? That's an honors course, seriously.
No, Chem 1B is probably going to be 2 papers. Yeah, not 3 papers. But, I don't know, did you look at the video? Did anybody look at the video when we talked about the paper that day? You did? And didn't I mention what I want to see in the paper? If you do that and you include everything I said on that video in the paper, that's an A paper, That's all, Rather, because if I keep showing you, okay, this is what was done, then I might start to think that's not going to be an A paper anymore. That's going to be like a B paper or A minus paper or something like that, But just put in, and actually you probably could see the sample paper in the video. Maybe freeze it and then see. I don't know if it's, maybe I need to do it in HD. But, with a little bit of effort, you just put those things. Now, you can come and ask me, okay, this is what I wrote for this. I asked you to include how do we get rid of the interferences. And you could show me, this is like the paper, in the discussion, it has to be there. And so, like, for example, in the paper I was reading the other day, it's not in there. How did you get rid of the interferences? And so think about that for your paper. And so if you have something like a rough draft, I'll be happy to look at it and tell you what you're missing, and to include that for an A paper. Put this in, put that in. Or just review that video one more time, and if I miss something in the video, let me know. But, basically I'm looking for specific things in your paper, and I'm just going to go down. Did you talk about this? Did you talk about that? Did you talk about this? And if you have all those things in there, and it's reasonable, that it shows a little bit of understanding of that, then you got it. You got the A. And so, like I said in the video, I want to see chemical equations, chemical reactions. And so in the last rough draft I reviewed, I didn't see any chemical reaction or chemical equations. So that's missing in your rough draft. Okay. Other things? I know we're over time, but I don't mind staying as long as you guys want to talk about. Or if you have to get going, but I understand that too. But make sure you guys can do those valence bonds, and make sure you draw the orbitals correctly, because this is something I don't want to see for tetrahedral. Something like this. What's the problem with this?
The shading.
Right. It looks like a trigonal planar, doesn't it?
Yeah, there's no shade.
Yeah, there's no shading. And so I saw a bunch of these this semester with no shading. So you got to shade it like this. No. In fact, what I greatly appreciate is if you could draw it, with the same kind of thing or the same orientation that I draw, would be nice. If you could just do this way, that would be a lot better for me.
How do we shade it? We have to add an SP2 onto the shaded one.
You could do two things. You could leave the SP2. Sorry, I have to turn this on. You could leave the SP2 unshaded, or you could shade it also coming out.
But the whole thing then, or because there are other
others
for it.
Right. And so that screws everything up.
So
that's why I don't draw the SP2 here. I draw the SP2 here.
But what if we have to draw it on like 3 of them?
Then you pick this one.
You don't have to draw all 3 of them?
When are you going to have more than 2 SP2s? In fact, why don't you get on an SP3, this scenario doesn't come up. Actually, on an SP3, only one SP2.
I think it's mostly on like organic molecules that it comes up where you have like those chains.
Okay, the chains, yeah, for the organic molecules with the chains, what you would do is you would just put it in here. And so here you have your SP2, so you could throw out, a double bond somewhere, whatever. But you just try to keep it in the plane. If you were to pop this out, you would be talking about something like, I don't know, on the past exam, did I have you do an amino acid? Glycine? Did I have you do glycine? On past exams, I've made people do glycine before, valence bond. And so let's do that one, because that one has sp2 and sp3. Oh, it does it. Amino acid. You know what an amino acid is? Amino acid has an amine. Did I talk about amines? Probably not. Okay. Well, let's just look at this. If I had a structure like this, this is not. If I had a structure like this, how would I draw this out? Because here now this nitrogen is carbon's sp3 and this is sp2. And so could I draw, or do I have to project the sp2 out? Well, here, if I were to draw this as a 3D Lewis structure, I'd probably do it like this. I put the lone pair in the plane and the first bond to the carbon in the plane. That means this bond to the hydrogen sticks out and this bond to the hydrogen sticks in. And so the trigonal pyramidal nitrogen I draw like this. This is going to an sp3 carbon here. And so for this sp3 carbon, I got to put 2 in the plane and 1 out. And so the 1 in the plane I'm going to put, because I have this in the plane, the 1 in the plane I'm going to put is to the sp2 carbon here. And that means this hydrogen sticks out here and 1 hydrogen sticks in here. And so I have that. And then this is an sp2 carbon, so I can just rotate this. Since there's free rotation about the single bond. And so I can just rotate this flat and then have this go to my sp3 oxygen. Now this sp3 oxygen, I'm going to put the hydrogen in the plane. So this is in the plane. That means 1 lone pair sticks out of the plane and 1 lone pair sticks into the plane. And so this is trying to show the lone pair sticking out, the lone pair sticking in this sp3 arrangement here. These 2 lone pairs here are in the plane. This lone pair is in the plane. So if it's in the plane, I just drew it like this rather than this. Now we can draw the orbitals out. Drawing the orbitals out, we know how to draw an sp3 set of orbitals on nitrogen. So 2 in the plane, 1 coming out, 1 going in, like this. Okay, then we have a lone pair in this one, and these 2 bond to hydrogen. For this hydrogen, we don't need to project it out. And this hydrogen, I'm dashing it. And so, you could shade this hydrogen if you want to show it's coming out as well, but it's not necessary. And then we have this going to an sp3 carbon here. Okay, this one's got to shade out, and this one's going to shade in. And so here, this one bonds to a hydrogen here. This one bonds to a hydrogen here. All right, and then this goes to an sp2 carbon. This sp2 carbon is bonded to an sp2 oxygen. This sp2 oxygen has 2 lone pairs. We've got an sp2 sigma bond. Then this sp2 bonds to an oxygen sp3. Okay, this sp3 orbital I'm bonding to the hydrogen. So that leaves this sp3 coming out with a lone pair, this sp3 going in with a lone pair. Okay. This. And then we show the pi bond. Like this, something like this. Maybe pi bond. This is called the valence bond.
Yeah. The first one? What's the structure like?
This one?
No, the left one. Left side.
This one?
Lewis structure?
Yeah. This would be the like the 3D Lewis structure.
For example, PCl5, we would need to draw a bunch of sp2s, sp3s.
For PCl5,
Yeah.
you have to draw a bunch of. Yeah, I did that
It's
before.
out of plane, but remember my original question, I how to shade it.
Yeah. So here, you put 2 in the plane, and then 1 going in and 1 coming out. like this. And so I'd shade it
But
like
I can
this.
only put 2 CL or 3 CLs in the
Okay, that's true. And so what you do here is this. You bring this one out, so this one's coming out. And so you put this one like this. So you could do this, you know, there are different ways. You could shade this like this, right? But now none of these are in the plane, right? And so what we do is we'll just do like this. We'll just keep drawing it, like 2 in the plane, 1 coming out, and 1 going in. So from this perspective, these 2 are in the plane, this one's in the same line as this one, and so it shows it like that. Otherwise, you're right, it gets hard to draw these. Yes. Andrew, did you have a question? You came in?
I have a question about the practices.
Okay. What's your question about the practices?
You don't fall in the forward try to serve from the, if you come out, 50% come out, 50% come in. If it's 50% come out, does that mean 50% come out and 50% ion?
Yes.
So it should be 50%.
Yes.
100% come out means 50 shares of the electrons.
Yes.
What about the electrostatic potential map is electron cloud, electrons, short density, electron orbits.
The electrostatic potential map, unfortunately, we didn't get to go in and to do Spartan.
Well, I chose electron cloud.
Okay. What were the choices?
Electron clouds, electrons, short density, electron orbits.
I think he fixed Spartan. Let me just check.
Andrew, which test?
Well,
Electrostatic potential map, I didn't really talk about. But we tried to generate these by hand. And so what do electrostatic potential maps show? The electron cloud, the charge density, and...
I wasn't sure about the orbit.
All right, let's take a look at the electrostatic potential map here.
Because it's just the probability of where the electron will be. It's not, it's
Right.
orbital.
Electrostatic potential map shows the whole composite. You know, when we're doing all the dots like this, you know, all that mess, all that whole mess results in the electrostatic potential map, showing a mapping of how the electron density is distributed in the molecule. And so it doesn't show the individual orbitals. And so orbitals, no. And so, let me take a look. What were the choices again?
Electron cloud, electrons.
Electron cloud, yes.
Charge density.
Electron density,
Charge.
charge density, yes.
what electron?
Electron orbits.
Electron orbits, electron orbits are ridiculous. Those don't exist, right? Electron orbits are associated with Bohr theory. There's no such thing as electron orbits.
It's orbital.
Right. And even if I said molecular orbitals, no, because the electrostatic potential map is all the orbitals. You know, the sigma 2s, the sigma star 2s, the sigma 2p, the pi 2p, all of that creates the electrostatic potential map. So we don't look at it individually, so it doesn't show individual orbitals.
Does it show electrons though?
It doesn't show electron. How can you see electrons? We don't see electrons, so it doesn't show electrons. It shows probability, electron probabilities, but it doesn't show electrons.
But you see a mass of electrons, so
Hmm?
you see a whole mass of them. If you see a group of people, don't you see one group, one person? You're saying that electron's too small to see, right? Which is understandable. All right.
You don't see the electrons. Nobody has actually really seen an electron.
Electrons can in a microscope?
No. Electrons are nothing like, there's nothing in the physical world that is similar to an electron. And so an electron is something very difficult to understand. Okay, I need to power this down, otherwise.
That's a question.
All right. I have to stop this.